All right, so hello everyone, we're back. My computer crashed. I apologize. Stream is back up.
All right, everyone. I'm not sure if you saw. Was there a break? This is just a completely different stream now, right? Okay, so I'll do the intro again. All right. Welcome, everyone. This is another Wolfram Institute Life Science stream, and we're back discussing sub-axiomatic foundations with Carlos. So Carlos has been doing some computer experiments, some different searches over SK combinators that he'll be showing us today. We also will probably begin to discuss further development of the theoretical framework for this study, since we're making nice progress in that direction. And because we've already made some nice findings and we're beginning to develop a more general treatment for making sense of those findings, it's now time to do some further literature review and become more familiar with some further theoretical concepts that will allow us to kind of properly frame this work that we're doing. But while we begin with some of these searches, I think
Yeah,
yes, we just began this. We just tried to do this stream, and then Carl was actually still doing a search, and then we crashed. So anyway, we're back. We're all healthy. This stream has begun. So Carlos, please go ahead and show us some of the work that you've been doing.
yeah. So actually, I was just to clarify. I was not running the search as we crashed, but I think the memory was somehow allocated or something, and the computer just didn't like it. It just died. Mathematica crashed some time before. That's what I meant. So anyway, and yeah, so all this section was full of stuff, and now it was in the last save, which was in the middle of defining this first function. Anyway, but so in our last conversation, I should say I began sort of reading up, looking at the things that theoretical background stuff that might be relevant, and considering all these things, but especially while things were running, because things are extremely slow. To find some. So it's either it takes a half a second, or as far as I could see, it takes forever. Like I let it run for half an hour, no results. So okay. So what was so last time we said that an interesting thing to look at experimentally would be the robustness of encodings of different functions. And so I basically decided to, well, first of all, very simple thing, give a random SK combinator encoding of a set of cardinality given and up to expressions of a certain depth. So, for example,
Okay.
this is a the SK encoding. I guess I have to compile this, and this is the SK encoding of, now it's a different result. It's a random thing. So two elements set with three, with up to depth three. So for example, I can do cardinality three. It's three. Can run it again. It will be different. I guess different. So you get this things, and now we could. So just to be clear that you can use the same labels as usual. If you just go depth one, it's just these symbols. There's only one thing you can do. So
So
yeah,
I guess my first question is the purpose of these functions just to give examples
yeah, yeah, yeah,
because they're random,
yeah, yeah.
or will the randomness be used in some way, or is it just basically to show instances of it?
So it will eventually, the randomness will have to be used in that we want to limit. I think I haven't tried anything beyond depth four, because there's, I think, in the order of 10,000 terms in up to depth four. There's around 10,000 elements in the list. So I've
It's actually not too 10,000 is not
no no
horrible.
no. It is, because you will see.
Okay, okay.
So because it's not the cardinality that matters. It's the fact that, these are up to depth four, and when you compose these things, you will see that it's ridiculous how long it takes. I won't be able to demonstrate how long it takes live on the stream, but you will see how it
Yeah,
blows up.
sure. Yeah.
But anyway, so yeah, this is just for demonstration, but we will at some point also just randomly sample from the pool of inert expressions. Now these functions here, yeah, these are initializations. So these functions here are basically adaptations of the functions that we had for because the functions we had that sort of searched for operations were actually tailor-made for the nesting of S labeling system. So what I had up here, all these functions, we search for operations like this one, right? Search for operations of cardinality for cardinality 2, arity 1, and depth 3. So these are all one array operations, right? Unary operations. They are all you at no point you have to say anything about how your basic set is encoded. So it assumes that this set is encoded in the successor function way, which takes just the list ordering of the set in Wolfram language and assigns k and then applies s of k, s of s of k, s of s of s of k, etc. Right. So these functions have been adapted to just work with arbitrary. These functions have been adapted to work with arbitrary arguments. So basically, you can pass the same sort of functionality. You can pass a list of expressions, which you want them to be inert SK combinator expressions, but technically could be any expression in principle. And yeah, basically these are some examples. So, for example, let's ask something that we know for reality check. SSK, we know it's and, right, in Boolean algebra.
Mm-hmm.
And here the argument, as you can see, is the two element set with the labels that we were familiar with, right? So if everything works as intended, we should get that SSK is a binary operator, right? So we run it, and indeed, and indeed that's a two-array operation, right? It gives it as a tooltip because it's better for than listing on bigger things and just picks out of big lists.
Okay.
So yeah, so this confirms that this is a two-array operation. Otherwise, it will output nothing. What is this one? So this is operations up to arity and depth. So this is these are the same operations that we had. So these are the same operations that we had before. And so unary, binary. These are the same operations that we found in the previous searches, but now the different, because I put k and sk here, but now what I can do is just change that. And so, for example, one thing that I tried is what if I put the second and third instead of first and second?
Yes.
So it hits some things, right? This is kind of curious. I mean, it hits something. And it seems to hit a similar number of operations for the same depth of expression, right? I mean, a little bit less, right? This is how many? 1, 2, 3, 6 in total, and this is only 4 in total. But there's some similarity there. So it seems that the first
and we still get SKK, we still get K, we still get SK, we'll get SKS. Oh no, these are all okay. That's interesting.
So
you have many of the same ones. Yeah.
So I mean, they are going to be the same ones because we're only checking for inert expressions. So the fact that they are the same ones actually doesn't mean that they are the same operation.
Right.
So this is something that can be checked directly if we want to. Whether but it should.
That would be fun. Right.
Yeah, they shouldn't be the same one, right? In general. Now, the other. So, I think the best use of time is for today is discuss briefly some of the points of the theoretical direction, so I can do the best job in the next few days before I send the summary, and perhaps Nick can help in identifying why this is so extremely inefficient, or why is it otherwise so expensive. I have a feeling that I'm doing something very inefficient, and it's not really that expensive, but maybe it is that expensive. It would be good to know. So
we could look at this. We could actually just take a look at the functions.
Yeah. So
even now or after this review.
Yeah. So here you can see, for example, this is just I listed all the inert expressions up to depth 3, and I just randomly copied some of these into the for a cardinality 2 thing, and I just did the same search, right? Like search for something, and so basically when you do up to depth 1, where you only check, you literally only search for K as an operator, and S as an operator,
S.
right?
Yep.
So K is always going to be found as a binary operator because
Yes.
we know how K acts, right? So
Right.
it keeps the first argument. So it's always, so K is always a binary operator that has constant value equal to the first element of your list, right?
Yep. First.
So
right.
Makes sense. It's good reality check. It means that function works well. But when I put depth 2, which, look at this, it's not that crazy. This is depth 2, right? It's up to three letter terms, right? This is depth 2. Because of the expressions here are quite long, right? So this is checking for things that are that, bracket, something in the list above, bracket, something in the list above. So these are quite long things, and it checks for all of them, right? And it has to run all the possible tuples of arguments. This particular computation that is here at least lasts for more than an hour in my computer.
That seems a little weird. Nick, what do you think?
No, what is particular? You're running to a fixed point, right? At some point.
Yes, I'm running the
Let's look up which one is the most hungry one.
So I'm running this. I think this is what takes up all the time. I'm pretty sure.
Yeah, that can happen.
Yeah. So because
for a simple expression, it can run like for thousands of steps.
Yeah.
What is the highest Steven found in his blog?
Oh, there was some kind of. Oh yeah. There's some analysis on the length of. But we don't have any certainty that these are somewhat shortest path or something, right?
Not necessarily, I think.
No, yeah.
But it assumes the left out order, so it should be always conflict, I guess.
Sure, yeah, it works, but not necessarily the fastest. But yeah, just to explain the complexity here, James, is that this thing basically puts the given expression into operator form, right? And basically just passes the different arguments, and the arguments are the labels that I choose. So for each initial step, it computes all the possible crossings. So when I say depth up to 2, like I did here, what it basically checks is the initial state of this. The initial state of any of these expressions, and then bracket one of these elements, bracket one of these elements. And these elements are these longer expressions that I wrote here. So yeah, some of those expressions as Nick said, might take like thousands of steps. And it doesn't.
Have you tried doing this with still depth 2, but just a somewhat shorter expression?
It's below. It's below. So I did it for like depth 1, which is trivial. It finds K instantly. And then for these 3-letter expressions, at least half an hour, no output, at least, or an hour. Like I left it for a long time.
It doesn't guarantee it will always end. It doesn't guarantee it. Even with the default writing order.
Wait, really?
Wait, you mean there's no guarantee to reach a fixed point?
Yeah. You can. I just found it in the Steven blog.
Oh.
The minimal size of a combinator when it happens, it's like just seven S's together, and it just exponentially grows.
Wait. Something. Wait. I was confused about that. So wait. So you're saying that this system is not universally confluent?
Well, that's my concern too, right?
It's confluent if it's not if there's exist one, then it always conflict. But if
You
it
mean
doesn't,
if there is a fixed point, then it'll
then the order doesn't
it'll
matter.
evaluate confluently to the fixed
But it
point.
also can happen that there is no fixed point. Yeah.
Oh. Okay. Oh. I didn't know
We
that.
haven't really addressed. Yeah, we haven't. I kind of even forgot about it because we haven't been looking at those kind of combinators at all. But yes, that can happen. Right. In fact, I'm scrolling through the combinator book. Yeah, there are combinators of this kind.
So
this makes everything a lot more complicated.
So I guess, I mean, intuitively, it makes sense that if your expression only has s's, there's no way that's going to be confluent, right? Well,
Nick, did you say that there's?
Depends on the expression. Sometimes it
no, it depends on the expression. Depends.
Yeah.
Depends.
Nick, did you say that as soon as there are 7 in a row, then what did you say about there being 7?
Well, the
S's
minimal
composed in a row?
example, Steven said he enumerated all of them up to size 6, right? And they're always terminating, right? There's always a fixed point. And the first ever combinator that is not terminating is when you have 7 S's. And there are 2 of those.
In a row.
No, just some combination of those, right?
But the example that Carlos has here, there's only 6. If you look at the first one that was aborted.
Well, but I mean, bear in mind there will be more, because it will actually hit at some point this twice together with, for example, this. So it will be like 8 S's. That makes sense, actually. That these two took forever. It makes sense because, I mean, some of these might be confluent, but there is S's here. And in particular, it tries to check for all the combinations, right? So you get. Nick, can you? Is the expression in the book?
Yes.
So I crashed and everything closed for me. Wait.
Find it. That minimal one.
Yeah, that'll be interesting to actually look into. By the way, combinators were mentioned twice in the conference. 2 different talks, I mean.
Like here. So the second one, the first one evaluates to the second one, so the second one actually goes. You can only consider the second one, and it just grows exponentially.
Let's actually see that, right? Let's see what happens. I'm curious. Let's do it here. So you're saying if I apply this thing? No, but this is bad, right? So I should use the graph function. Give me a sec.
Either graph or just nest it.
Nest
list.
Yeah.
For replace all and see how the expression changes. The same kind of replacement, but not the repeated one.
Yes. Let me just get the thing that does it, because I want to control the steps, obviously. Okay, so let's take here. Let's run it for what, like 3 steps to begin with. Oops.
You don't have to do it in multi-replace fashion, right? It's a little bit more than we are trying to show.
Yeah. But I want to see it multi. I mean, why not? I mean, we're not going to compute a lot of steps.
Okay.
3.
Wait, what? Too many already? Maybe there's only one way. Makes no difference.
Maybe.
It's growing.
Oh, it's still linear, I think.
Just remove the labeling.
Oh, yeah.
Well,
it's linear.
Isn't the point to look at the labels and
Yeah,
see how
it is kind of the point.
the expression size is growing?
It is growing, for sure.
But
Well, what do you do with the length instead?
Nick's making
Oh,
the right point, though, which is like this thing is single way. We don't actually need to look at it as a graph. We
Sure.
can just evaluate. Yeah.
Sure.
Just evaluate its steps.
So let me. So that was the. Give me a sec. That was the fixed point.
Well,
Just nest. You just nest and you replace all.
what about just combinator evolve, right?
Yeah, you can use that. But you have a replacement rule. It's just a simple replacement.
Yeah.
Either way,
It is. Let's so nest. Yeah, let's nest with
Replace all.
replace all.
Just put a rule.
Take the rule in list or not.
Doesn't matter. You just need a single rule anyway. There's no case.
Sure.
Right.
Like argument like this.
Yeah, just a operator for.
Operator form. Yep.
And
Into the initial state, right?
also, it's a second argument to nest.
Okay. And then
And then how many times you want to do it? And if you want to make a list, then nest list.
nest list.
Yeah.
Those are the 1, 2, 3, right?
Yes.
Oh, it's 0, 1, 2, 3, I guess.
Wait.
Yeah.
Yeah, that's the initial state, I guess. Oh, cool. Okay, so let me do the. Yep. Okay, sure. Yeah, it grows. Okay, that was interesting. I didn't actually. But it makes perfect sense in a way that this should be plausible because S is kind of additive. Okay, well.
So.
But that doesn't really change anything in a way.
Well, the question is how to set up these searches where, when possible, you can ignore these cases or, ensure that you don't get these growing evaluations caught in your actual search. You're basically just interested in ones that do, at some point, converge to a fixed point.
What I think would be useful is that I was thinking about this because currently we just have this depth control where, this is the explained here. Here? Sorry. Oh, here. So basically the realization that because we are after inert expressions, any pattern that is smaller than the rewrite rules themselves, that it's going to generate all the inert expressions, right? By compositionality, right? By putting things, by applying, basically. So that's what this function does. The inert combinator at depth. So what I think would be interesting, especially now that we need this control, because at first I just wanted this control more for my clarity of mind, but I think now it's actually technically relevant that we have a way to determine, so give an expression, so generate all the expressions that involve a fixed number of S's and a fixed number of K's, which should be a fairly easy application of like 3, it shouldn't shouldn't be too complicated.
Sure.
Do you both agree that that's a sensible thing to do at this point?
Yeah, you just wanna filter out the list you already have, right?
Yeah, I want. Yeah. Exactly. Yeah. But maybe it's even. There might be a faster way because this depth generation, I think it's doing a lot, and we don't need 10,000. We don't need 10,000 labels to start doing some experiments, which is depth 4. But we do need more than like 5. That is what, or 6. That is what we get in depth 2, right? And in depth 3, which was this, where was it again? Sorry.
But it's only increasing. You don't have to look up like too many depth in order to just filter out the fixed number of S's and K's.
Sure, I guess so. So yeah, you could just do it on top of that list. Yeah, I mean, I'm not disagreeing with that. I'm just wondering that maybe we don't need to generate that list and we could just make the trees to save time, right? Just generate the expressions that you need instead of searching for them.
Sure, you can put this condition in your generation there, in your function that generates a fixed depth.
Oh, really?
You can always check. Don't insert your argument if it exceeds the size that you want.
Yeah, right.
Something like that. Then you only generate only number of SNKs that you want.
Yeah, we might need to meet tomorrow quickly and sort this out.
This is like a kind of ugly code that I wrote. Can do better.
Yeah. Let's discuss this because
line. Yeah.
Yeah. We'll do it tomorrow in a moment. Yeah. Because I mean, I will also try to do it just applying the tree functionality and because it's a good thing for me to do to be able to just code generating all possible trees, and then you can give me your efficient one, and that's going to be very good.
Well, trees expression, but it doesn't matter in this case.
Yeah.
Right?
Yeah.
What do you need?
No, but I mean it.
I think Carlos just wants to think about it in terms of trees, maybe even heuristically helpful, maybe.
I mean, it's just to do a systematic way of, because otherwise, because I'm not super used to mathematical expressions themselves, like I don't know the functions that do all the good things that I want them to do, but I know exactly what I need to do in terms of trees. So
that's what I mean when I say kind of maybe helpful heuristic, even though Nick's thinking about it in a different way. Can we do something? So just to kind of review, okay, we've discussed some of the challenges that you've encountered while doing these searches, but can we just summarize, especially since we don't have a nice recording from the last stream, let's just review the goal, the objective of these searches, what you're looking for, some of the other searches that you want to do. Let's just kind of
actually let me briefly mention the things that were deleted here. So I decided, I mean, this is going to be a problem anyway, because the issue, I mean, if the issue was the ones that were going exponential, then maybe there was no issue. And I mean, if we go big enough, it's going to be an issue, obviously, but yeah, anyway, what I was going to do here was a smaller search that instead of systematically going after general operators, or general operations, was to try and look at one particular operation, identity, and just study that operation, right? As an example, to look at across cardinality and across labelings. because the identity map is the only map that you always know you have in a set, right? So it's an operation that we know always is going to be encoded. I mean, mathematically, you cannot really argue that. Well, I guess you can argue that if your set is finite, then you can do some finite thing. But the only operation that you can ensure it will exist is the identity on a set. So the function I had, unfortunately, is gone. Did exactly that. So is identity sk basically took an expression and a list of arguments, which basically was the encoding of a set of a given cardinality, and just tested whether that is an identity or not, and then you can just systematically check for all expressions whether something is identity or not. So, but I mean, I can just recode that in a couple, half an hour or something.
Let's just review for this case and even for the case above.
Yeah.
What in particular are you looking for?
Yes.
In the circuit.
So the goal here is to try. So first of all, see how sensitive the
Yes.
nest S encoding is to this framework. So that my first analysis is going to be in terms of cardinality. I'm not going to look into anything like equivalence between encodings or anything like that at first pass, right? The first pass is going to be purely based on cardinality, so just counting.
Well, so let's say you begin with KSK, which is the default.
Yeah.
Okay, great. And now you've considered something slightly longer encodings, SFK and SFK, and then you've tried to do these rather elaborate encodings, and you've probably gotten smacked in the face by infinity, but we can kind of figure that out. So, but let's say that becomes tractable. So for one of these examples that you had to, one of these searches that you had to abort, let's say those searches actually yield fruit. How are you going to examine the outputs? What's the systematic way for actually making sense of these results?
No, that's the point. The problem was that I was hoping to have some things to go off of, but I couldn't produce them, right? And then to try to play with them and be able to tell you, yes, these are good things that I could do with them, because I have no idea how different they're going to look like, right? If, for example, if we assume they look homogeneous,
go ahead.
Right? If we assume they all look homogeneous in some sense, like they output that similar cardinality per arity, in some sense, then you could just simply identify. There's several ways to do it, but you could simply identify enumerate all the operations per arity, right? And so how many? You have 4 in unaries, 16 binaries, whatever, and just enumerate them or label them or whatever, and then just look at how they are distributed in terms of different encodings. And you can be systematic with the encodings, or you can just be random with the encodings and generate like a 2D distribution.
But what's the distribution is over what? Over the length or?
No, the distribution is over the. So you have basically 2 variables, right? You have the encoding that you're using, which some list of combinatorics of a list of inert expressions that seem amenable or are, we don't rule out because of infinities or whatever. Some good inert expressions. That's just a list of pairs, right? And the other variable is some list of enumerated operations on finite.
So I understand that, but I don't understand if you're actually going to compare them, there have to be values that you assign to those. So let's say you're toggling your encodings. What as you're toggling those, what's the actual?
But there's no value. So it's just value. A boolean. There's no value. It's just 1 or 0. So you have.
No, that's not what I mean. What I mean is if there's a distribution.
It's a distribution of values. I call it a distribution because it's a matrix. It's a square matrix or a rectangular matrix. So you will compare the vectors, rather. So for an encoding, okay, given an encoding, you have, the entire list of possible operations, and then you have all the possible inert expressions that might encode the operation. Sorry, it's 3 axes. So it is a matrix. Yes, sorry, it is a matrix. What I meant. And then the third axis is all the possible encodings, right? So, for fix an encoding, like let's look at this example, right? Fix an encoding, which is this KSK, like the standard one, right?
Sure.
Then you have 2 variables, right, left. One is the axis of change what operation you're looking after, which is just going to be a posteriori thing that we find, not something that it's actually a variable that we control over. But you have another axis, which is all the possible inert expressions that you want to check that might encode your operations. And so
yes,
you're gonna check for all of them, all the ones that we deem relevant, and you're gonna get hits in this, right? You're gonna get hits that, oh, this is the identity, this is the anti-identity, this is the whatever, and this is whatever, right? You're gonna get hits, and the point is that this is going to, for each encodings, you're gonna have a matrix of we up to a certain number of up to a certain arity and up to a certain length of expression of SK combinators. That's a matrix, right? That's just hit zeros and ones. And so the idea is, for each encoding you have a matrix, and then you can just do it for many different encodings, and you just compare matrices, and you can define some distance between matrices if you want, or something like that.
So what are you comparing?
Matrices.
Zoom out for a second. What's the point of
the point is
really precise?
The point is to compare the sensitivity of operation distribution according to the encoding.
So I understand the basic kind of question, which is, let's say we change the coding.
Yeah.
How does that affect these functions up to some, or the operators that we get, where we're toggling it according to cardinality and we're toggling it according to arity, right? So that's a basic qualitative question. The more quantitative question is, as you're getting results for these different operators, so let's say, for instance, you get some operators and they look more or less similar. Maybe in some other case, the operators are more elaborate. They have they require composition of more S's and K's, for instance. So let's say you happen to change the encoding and you get some list of operators that's quite different. Let's stay qualitative for a moment. What is the conclusion that you reach?
No, I mean,
one way or the other.
I'm not because so you could, and on top of everything, you could consider numbers of S's and K's, or depth of expression or length of expression in some technical sense, as added sort of metric on top of things. But what I was suggesting wasn't qualitative. It was quantitative in the sense that you would compare So it was quantitative in the sense that you can compare two Boolean matrices of the same size, right? And it's a matter of what is a good criterion of comparison here. And so is it some distance that you want to define? Is it because these things are infinitely big, technically. I mean, if the actual whole thing is infinitely big. So you take a chunk and you effectively have this pixel image, black and white pixel image, and it's just a matter of how different they are. You can use some matrix distance, image distance. I mean, the thing is, it's going to be quantitative. Like it's not some kind of conceptual idea of like, oh, they're more or less similar. It's going to be a metric that you extract, but what you're measuring is some kind of superficial, still kind of, are these more or less similar encodings, right?
So then the question is, so let's say, okay, so we have these matrices and we're computing their distances, right? But what's the significance or the meaning that we're assigning to those distances? So let's say the distance is great, right? Walk me through what would we conclude from that finding?
Yeah. So imagine. Okay. So the best way to answer that is to imagine that the distance is 0, meaning they are the same.
Fine. Right.
So
Okay.
if we actually found 2 matrices that are the same, that would be
Yes.
quite interesting in itself, because that means that you've changed 2 encoding. You've changed the encodings
Yes.
of your labels, and nothing has changed, right? So you have exactly the same encoding of. I mean, I think that's impossible. You can argue that's impossible based on the fact that combinators rewrite us the way they do, but it seems intuitively clear that that shouldn't be the case. But I don't know. Might be possible. Who knows? But that would be very, very interesting. I mean, I'm guessing that's not going to be common. So you want to somehow measure how far you are from that situation. So that's the meaning I would attribute to distance, because if you have some kind of so if you have expressions that have sub-expressions that operate in a certain way, then it is likely that you're gonna reproduce some behavior in some parts of your encoding. So maybe there can be sub matrices that are the same, because if you put case cleverly, you're gonna kill the arities up to 3, and so up to 3, all the arities are going to be kind of empty and nothing is going to happen with this particular encoding. And then after arity 3, things are going to be different. So you're going to have like a chunk of the matrix that is the same, because case.
I want to zoom out even a little farther. I mean, I think part of the point here is that if we take what we've been kind of calling Boolean algebra, that we have not actually model theoretically, I believe, really found Boolean algebra yet. In part, that's one of the objects of this overall study. But let's say we take Boolean algebra. We have done what we've called an emulation, and that involves encoding something like truth and falsity values.
Yeah.
Right. And so when we emulate these different operators according to this specific encoding, we found that they evaluate convergently, confluently to one of these truth values. So this kind of emulation, so to speak, is informed by that encoding. Ultimately, if you change, so one of the questions is, if you change that encoding, in some sense, it's a different emulation in that the operators might. I mean, so one, at the very least, truth and falsity will be represented differently in combinators, and then the question is, do the operations themselves also change? This is one thing
we know that
you'd want to know.
We know that already. We know that the answer is they do change.
That they change, but to what extent? And is it the case that what is an operation that is and under one regime is now or something else under the other regime? So I mean, in part, when you're switching the encodings, in some sense, when you're actually searching for these operators according to encodings, in some sense, you're getting the operators that you would use say emulate something like Boolean algebra under some particular encoding. So this is something of the bigger picture. But then the question is, again, if it was the case that the operators were always the same, then I guess you could conclude something like, well, you can pick these different arbitrary values for truth and falsity, but for whatever magical reason, it happens to be the case that the operators really never changed. That would be the case if the distance was always 0. But on a foundational level, what does it really mean if you find that so you're expecting, and maybe we already know, that the operators will change, but what's the what are we really testing?
Yeah. So what we're testing is exactly the fact that you have this model theory informs you that certain functions, certain operations always exist on some sets, in particular identity. That's why I was searching on identity. We could do things like always. I think that it is true. I mean, this must be true. I don't know for sure, but it must be true. There's always an associative operation in any set of any finite cardinality. So we could also say, let's always find an associative operation on a given set, and that operation is one. It's a model, right? So it's exactly one. It is a full value table. So what we can say, so these are from the model theoretic side of things, we have these things like platonically they kind of exist. They are there, right? A set of a given cardinality and an operation, that's a well-defined platonic object, right? And so the idea is in the SK world, those things we know for sure already they have multiple encodings, and the encodings change both in the direction of, for a given labeling of the elements, you have several expressions that operate that confluently rewrite to the correct values of the same operation, and if you change the basic labeling, you have another instance of that, which in general we've seen it's different. So there's a huge diversity of SK combinator implementations of the same platonic object that we are calling this, finite set operation, right? So so the point is in the search is that let's make, because so far we haven't really systematically identified this. I mean, when we were doing the more sort of Boolean language thing, where we had the explicit language of Boolean algebra, we did label things by and, or, and so on, and that's why I kind of focused on let's do and let's try to get patterns in and so on, and all these graphs, because now, I mean, we could literally, if you want to be still closer to Boolean algebra, I don't have a particular preference. We could literally go, and choose some like and, or, NAND, whatever. Choose a few, and just try to map out up to some sizes or whatever how the dependencies, and the first dependencies are going to be just these big arrays, these big Boolean arrays, and after seeing what those big Boolean arrays look like, which contain all the information we might ever hope for and want, then we can start to think, all right, so maybe just distance of Boolean matrix doesn't make any sense. Maybe let's look at something like length of expression. Let's look at number of S's and K's, or let's look at something that is a lot more specific. Because, I mean, we could start throwing cardinality numbers on top of everything we do, because these things are trees and they can be counted in several ways, and you can assign metric sizes in different ways. But at this point, as you're saying, we only are at this level of, we know that we can emulate model theoretic operations, and we know it's highly non-unique, but we don't know much more than that at this point. So all this story is to try and get something that is more systematic, that for example, controls over what operation exactly you're encoding, which is to say, let's give them either names and whatever, or some code for the enumeration of operations, and just search for them, explicitly search for them, because so far all the searches are kind of blind. They're hitting everything that works.
Yeah. I'm still searching for something of a bigger picture. You said something about dependencies that kind of interested me. I mean, it's like, okay, we have something like Boolean algebra. We have this particular combinator rewrite, but there are really many of these, and yes, they're going to be informed by these encodings at the beginning. I'm repeating myself. Is that like we suspect that they're going to be different, but it's still not clear to me. I mean, let's say you find differences, and we start to measure distance between them, or we're comparing them, and in some sense they're different. Zoom out all the way to this kind of study of foundations of math. What is the significance of these things being different at a deeper level, at a higher level?
Okay. I can elaborate on that for sure. So you can imagine at this higher level that if we want something that will be in this summary, right, in this proposal summary for more theoretical foundations in this particular project, we want a notion of emulation, right? This is one of the essential things that is important. So this non-uniqueness is basically the phenomenon you want to control when coming up with a definition of emulation, because you can always emulate a system by itself, right? And you just put the same copy of the rewrite system on the left and the right, and then certainly you emulate a system with itself. It sounds very trivial, but this is actually important, because what it means is that by emulating a system with itself, you're noticing something. You're noticing the fact that you have a bijection. You're noticing the fact that there is extensive mapping from one side to the other. These seem like trivial observations, but the point is that when you go to SK combinators, you actually have a situation where this is no longer the case, and you know this is no longer the case, and so you know that you're in a different setting. So what I'm trying to say is that if a system was just explicitly a subsystem in a way of another system, so you could inject it into it in a way, then you might actually not be able to know that you're injecting into anything. You might just think, oh, I'm just emulating the same system, because the only initial states that I can generate are somehow the ones that I already had. So the whole point of having, so we have one example of a system, this SK combinators, that does a good job of completely redoing model theory just by using the rewrite rules of SK combinators, right? So we know this works, and we know it works in a highly non-unique way. So the definition of emulation is going to be something that controls over this non-uniqueness, because I mean, the point of making the point that a system emulates itself is not a joke. It's to say that that's a good definition of emulation. It's a valid definition of emulation. A system emulates itself. So that is the strongest definition you could ever come up with for emulation, that you literally just need the same system twice, right? But you want something that is better than that. So you want something that's more flexible. And I don't have many examples of other systems that I can, if I had a wealth of systems that I could start to map between themselves, then I could propose something else. But at the moment, I only know SK combinators do a good job at capturing model theory, these operations in finite sets and blah, 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 or arithmetic or whatever. So to me, it feels important that within this very specific setting, we should get some general sense of so start to put constraints to the non-uniqueness that at this point just seems like a long list of non-uniqueness, and I want to put some structure to that list, basically.
So hold on. So we begin with the case of auto emulation, self emulation, and this is a nice bijection. Now, what we find in these other cases, like when we're going from Boolean algebra, say, to this particular SK combinator rewrite that we have, is that we no longer have that property. Now, really, I'm inviting you to be kind of as explicit as possible, right? So, but tie this question of uniqueness. So I followed you, except it's still not crystal clear how this question of non-uniqueness fits in. So I understand. Let's go. Okay, we have self-emulation. Now we're considering this broader emulation.
Wait. So it's not that we have self-emulation. Let me be clear with language. We are trying to define emulation, right? We don't know what emulation is. What I'm saying is that there are obvious candidates for definition. One definition is to say that only so-called self-emulation will be the definition of emulation. And we certainly want to cover that case, but we don't want to limit ourselves to that case. And what I'm saying is that the only evidence I have, and this is maybe because I don't know enough about rewrite systems and I haven't really worked on this for a long time, but the only evidence I have is SK combinators emulate in this user knowledge way in which Stephen did the thing, we did the thing, and we know how it works. Arithmetic, model theory, blah blah blah, all those things, right? But what we know is that even in our user level understanding of how the emulation works is non-unique, right? So what I'm trying to emphasize is that this is already different from the situation of the trivial self-emulation case, and so therefore the only thing I can observe is trivial self-emulation or emulation in some user level understanding that is highly non-unique. So the only thing that I'm really noticing is the non-uniqueness. I don't see anything else between those two cases. Give me a system, self-emulation is there. Give me Boolean algebra or model theory for these finite sets or whatever, and SK combinators, and then I find some correspondences, but then the correspondences are highly non-unique. So at this level of my knowledge of the problem, the non-uniqueness is the only real thing I can study because there's nothing else, right? I mean, okay, there's lengths of expressions and putting metrics on length of expression. I should say that that's another thing that you could also study, and complexity and length, computational complexity, Kolmogorov complexity, things like that can also be studied. But I feel it's much more parsimonious to begin with simply the enumeration and the sort of the set level, the collection level of things, and try to parse by stronger filters than just the complexity of expression. Because let me put it this way: I'm trying to do as much work as possible without having to go into the expressions of each of the states. We can always go to the expressions of the states. We can look at the expressions. We can count the number of cases, look at the length, the tree size of different kinds. We can do that at any time. Sure. But I'm trying to get as much out of this system without having to go down to the fact that these are SK expressions with brackets and whatnot.
So it's okay. So
in a way, I would say I'm trying to be as multi-computational as possible.
Right. Well, so it's like we've proposed this notion of sub-axiomatic foundations, but we've just picked some, perhaps minimal, but nonetheless, in some sense, arbitrary encoding. And so it's incomplete and not foundational to just say, well, we have this particular encoding, and we're going to study, the properties of what we're calling emulation under this encoding. You're suggesting, look, the encodings are non-unique. You can pick really arbitrary values for true and for false. Now, there's still going to be some structure probably there in the sense that, so you have these different operators, and this operator is and under this particular encoding. It might also be and under this particular encoding, might be and under this particular encoding, or it's not used at all as an operator in some particular encoding, or it's used as a different operator in some particular. But there's some more abstract structure underneath, which is you can do this. And it's like, it'll be, there's some pairs of S and K, SK combinator expressions that can serve as encodings for these different emulations, and they have corresponding operators, and there's some relationship between these particular encodings and these different operators. And so there's some kind of object that is more general than just selecting some arbitrary encoding. Instead of having to say, oh yes, we've built up Boolean algebra from this particular encoding, you can say Boolean algebra can be emulated by all these different encodings, and we've kind of formalized this is that object or some sort of structure which we don't understand yet, and we can say, we've determined the structure, or we're proposing that this underlying structure of these different encodings has these properties, and we found these properties by doing some computer experiments. So, this is not the complete structure of these possible encodings because it's infinite, but we've done it up to this cardinality ceiling, we've done it up to this arity ceiling. This is what it looks like.
Yeah.
So I mean, yeah, right.
Something I should remind everyone, especially they're watching, is you said we try to be foundational, but then we find this non-unique. We are being as foundational as we can be, in a sense, in that we're doing finite computational experiments. So in terms of mathematical foundations, we are never foundational in some sense. So we are being as foundational as we can be, in that if we have a way to operationally select elements from model theory and implement them in a well-defined computational framework, that's as good as it gets for foundations, right? And so understanding the non-uniqueness is like saying, I need to build a machine to, climb this mountain or build this arch or something. And there are many ways in which you can build that machine. so understanding a non-uniqueness is like saying I have to build a machine in some generalized sense, right? So that's I mean, we have kind of a prototype of the machine. It kind of works already. Okay, we have this as an example, but understanding that for a foundational program where you're actually trying to say, well, how much do SK combinators know of model theory? How much information do we have to affix to just the blind SK combinator universe for it to know about model theory? And to me, the best answer I can give at this point is to say, well, how are we parsing this non-uniqueness of choice that we already know how to apply in each of the cases, right? Each of the cases works as an emulation. So to understand that non-uniqueness is going to give us hopefully some better control. And then on top of that, related to the summary and the more theoretical, bigger perspective, also to start to wrap up, is we have the goal eventually to be able to, given two formal systems, tell, these are the kind of relational statements you can make about them. They don't talk to each other at all. That's an interesting phenomenon, right? Like they can't be emulated at all, right? That's interesting in itself. So you can start to think about how does it depend on the substrate for the states? How does it depend on the topology of the multi-way systems within the formal systems and so on? So, all the possibilities are interesting, but at the moment I don't really know what else to do than experimentally other than given the known case, let's try to parse the non-uniqueness and the what is right now a long. So basically what I have in my mind is that right now we have a very long list of things that do things in an equivalent way, and we have ways to actually parse that list and give it a structure and make it more into an array instead of just a list. And so when we get a list into an array and the array into something that looks more Boolean, and then start to compare, then things look like knowledge. It looks like we're making progress from chaos of a list that is just a plain no structure to something that has a lot more structure, right? So anyway, that's on the front of experimentals and sort of running things computationally. How I would proceed from here, I would try to get as much control as possible from model theory, given the names or NAND or whatever we decide, and try to make it as deterministic as possible within this framework. And theoretically, what I would try to start to do is, following all your suggestions of what theories might be relevant, is try to, pinpoint which area of the landscape of the mathematical traditions we need to somehow set camp to be able to start to make statements about these things, right?
Yeah, right. I mean, my main concern is that there are all kinds of particular computational experiments that we can perform, but I'm increasingly of the opinion that we need to have some sort of stronger theoretical framing for what we're doing. Not necessarily because it will actually inform the way the experiments are done, but because it'll allow us to interpret the experiments, and it should in some way drive or inform how we use them, and perhaps how we actually kind of build upon them. So one of my main concerns that I expressed in the email that I sent out is, I think part of the original motivation for this was just the nice results that we already had, that we could emulate these Boolean operators with SK combinators. But I know that combinators themselves, they do fit into this greater metamathematical tradition that's already there. So one thing that we haven't looked at, and I'm not sure to what degree it's even really explored in the combinator book, is that there's this deep relationship between combinators and lambda calculus. And there's this whole thing on, the Church-Rosser theorem, and these kind of general properties that hold for reduction rules. I don't doubt that what we're doing eventually through the experiments, et cetera, we'll have something nice and clean that we can say, where we could show it even to people who work in foundations of math, that makes some actual non-trivial contribution to foundations of math, where it's you have these particular axioms, but you can emulate these axioms at this lower level, and here's this kind of actual kind of mathematical structure that we're defining, that we formalize, that kind of sits below these particular axioms, because you can think about the axioms in terms of abstract rewriting, et cetera, et cetera.
Yeah.
But I guess I have this kind of sense of, it's not cautiousness, but it's like, I just have this feeling now that we've done all these nice experiments. I just want to make sure that we're very strategic and thoughtful in the experiments that we do at this point. And I think the way to really make sure that we're using our time and our resources in the best way is to really understand how combinators, because again, Stephen did all this really nice empirical work on combinators, and there's also this kind of historical piece on where combinators come from. But what I need to understand, and maybe there are some hints in some of this historical work that Stephen has done, though it seems somewhat biographical. I need to really understand how combinators fit in to with respect to this early work that was done by Church and by collaborators.
Yeah.
Nick, do you have anything to say about this? I mean, to kind of summarize, the main thing I want to avoid is we run a bunch of experiments and we get all these findings, then someone says something like, oh, well, yes, from Church Turing thesis, what we know about lambda calculus, what we know about combinators, this stuff is all kind of trivial because yes, we know you should be able to do these computations. You haven't kind of provided anything new. But it's not clear to me to what extent people have used those findings, like these findings at the kind of very early stages of metamathematics and the study of computability, et cetera. It's not clear to me how those have been used to actually try and dissolve this notion of axiomatic mathematics. I mean, in some sense, even this is what I guess people like, it's not unrelated to things that people like Gödel have done. But from what the work that we've done, it becomes so obvious that axiomatic mathematics is really something somewhat arbitrary, and the term I use is artifactual. I mean, it's kind of this human artifact.
Yeah.
But it's not clear, and so, but I guess it's like, it's just as a sanity check, it's like we should really make sure.
Yeah. Let me just add briefly.
Yeah, go ahead. Yeah.
Let me just add briefly that I completely agree with that. I completely agree with that we should check the theoretical context. I mean, I am not familiar with the side of logic, foundations of mathematics, formal languages, this kind of tradition. I do know, though, in the holy triangle of correspondences of univalent foundations of mathematics, I do know the category side and the homotopy theory side of things, and I know that this entire philosophy of rewrite systems as foundations or computation as foundation is kind of new, right? It's not that we're gonna end up just producing something that is happens to be derivable easily from whatever existing theory. So I absolutely agree. We should know the context. I'm just kind of reassuring you that as far as I can see, we are very much under charting new territory. That the fact that we are just having a sense of relationality between rewrite systems as things that we are sort of conceptualizing as a whole, that's already completely new. Like you can't find any literature on that. So I'm just to like frame it in a much bigger setting than, because if we obsess with the particular tradition of foundations of mathematics that comes from late 19th century formalisms and things like that, it becomes quite sterile, because those people want one thing very specifically. I don't think that's all of mathematics, even if they call it foundations of mathematics. And a lot of people don't agree as well. Like nowadays, a lot of people agree that mathematics is much wider than what historically foundations of mathematics claim mathematics to be.
Sure.
So anyway, just
sure. Right. But nonetheless, combinators, they did arise in a certain context. We are using reduction rules. There are these obvious relationships to lambda calculus and back to Church-Rosser and Church-Turing, etc. So it's what I just want to make it. I want to make it possible so that for the people who happen to know or care about that stuff,
I agree.
there's some because you can imagine there's some interesting kind of narrative here, which is axiomatic, like the kind of axiomatization of mathematics and this kind of rise of the study of computation. I mean, they weren't exactly contemporaneous, but they actually didn't happen that far from one another.
Yeah.
And so it will be interesting if now in hindsight with more computational tools, etc., if we can make as part of what we do this historical kind of argument, which is like you take axiomatic mathematics, you can actually emulate it at this kind of lower level. Part of one example is SK combinators, and here's the kind of relationship between SK combinators and lambda calculus, et cetera, et cetera, et cetera. But I think the key thing to be done there is part of the appeal of axiomatic of the kind of axioms is still somewhat of a kind of a neat, concise way of I mean, it'll be neater than the kind of obviously than the combinator version of it. And so I guess what we are hopefully going to get at the end of this is we can say you can go a level lower than axioms, and here's that system or that object or those relations underneath. And yes, if you want, you can explain it in terms of combinators and lambda calculus, etc. But from even doing computer experiments, which is kind of our novel way to address this, here's our kind of outline. And with time, it'll probably be some combination of actually doing mathematical proofs and plus using computer experiments to gain intuition. Here's our kind of description of, it's not exactly, they won't exactly necessarily be categories or quivers or graph algebras or something, but it'll be, here's some sort of object that's composed of these different kind of emulation, regimes with just different kind of rewrite systems with different encodings, and they have relations between them, and they have some structure, and you can view this kind of general. It's not exactly clear what it is. I mean, the kind of the cheap way is you could say it's basically some sort of category with these kind of the structures, but we want to really
it's category like thing. It's got
we have the liberty to kind of to define what it is, but that would be the nice thing is underneath axioms sit the structure, and if you want to, you can describe it using these tools from like Church-Rosser, etc. You can also think about it this way, and this is like kind of a more foundational object. See, once it's like that, then that's the kind of a thing where even your colleagues who attended the event that you attended today, it's kind of, I just want to make sure that we find a way to do this where I don't want to just show people a bunch of experiments. The experiments are really important, of course. And experimental mathematics is something that should be more popular, but it's actually building up these objects to these systems that we can describe foundationally. And when we need to, like I was saying before, it's like even referring this back to automata theory or these different things that have these different hierarchical levels, is like this is at the bottom of the hierarchy for automata theory, etc. And we find this kind of general object that's there. Just finding a way to experimentally gain the intuitions to build something that we can then describe using language that other people actually understand. That's the way that we can actually make this something that is compelling to other people.
I agree. So I'll try to reflect this as much as I can in the summary, for sure.
Cool.
All right.
Nick, do you have? I mean, Nick has been basically just sitting here. I mean, Nick, do you have anything you want to say about? Actually, how much do you know about Church-Rosser theorem, lambda calculus, SK combinators, the more theoretical side of abstract rewriting systems? Because we're about to kind of.
Well, not really, not much. Yeah, just on the practical side, mostly. I don't know what are the theoretical side of those are.
I mean, I think the person who took the greatest interest in this was probably Jonathan. I think even like if you go to I think there's an entry for the physics project on Wikipedia, if I remember. So like if you go to Stephen's Wikipedia page, it'll say Wolfram Physics Project, and it says Wolfram Physics Project, blah, 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 effort to reduce and explain all laws of physics with a paradigm of a hypergraph that is transformed by minimal rewriting rules that obey the Church-Rosser property. That has to be, I don't know. That doesn't sound like a Stephen description. That sounds like a Jonathan description, probably.
Yeah.
So anyway, yes. Just
Church-Rosser property is the same as confluence, right?
I think so. I think Church-Rosser is just confluence in some sense.
But it's at least as I've seen it, it's something for lambda calculus, or just when you're applying reduction rules that you will achieve confluence.
Okay, so I will confirm this, James.
Yeah, go ahead.
I will confirm this, but I think the Church-Rosser rule or Church-Rosser property is a much more, without wanting to sound disrespectful, short-sighted version of just general rewrite system confluence, because the systems that property was applied to very special systems that, from the perspective of general rewrites of hypergraphs or any kind of compositional system, the systems that they were studying were quite special because they were formal languages of, like, lambda calculus is studying quite special systems. But let's not get into this because this is an entire other theoretical discussion of a couple of hours.
Well, right, but the question is particularly for reduction rules. This is something that I'm embarrassed to say. Like, I need to fully understand, like, the abstract elimination that's used for SK combinators, and just just understanding these, like, alpha conversion, beta reduction, eta reduction. I mean, there's this whole kind of much more fine.
Those are simple.
Yeah.
Some of them is like just definition. Some of them just wrap a lambda around it. Something, yeah. Something like.
Yeah, we'll definitely get the context. I mean, I'm not saying no, but I'm just giving general comments of hope and excitement. That.
Good. That's great.
All right, guys.
Well.
Good stream.
How much?
We've been live for an hour and a half.
Well, so I think I've been trying to set aside 2-hour slots, just because we've been doing it for an hour and we always go over. So just so kind of viewers have better expectations.
Yeah.
But people have been participating in the chat. I do want to at least acknowledge them.
Sure. Yeah, please. I can't really change the screen because of not secondary screen, but I can.
So Willie Yam, I guess Will I am says emulation is entirely a semantic issue. Semantics lies outside syntax. You cannot define semantics without having some sort of observer that has its own language. The emulations are always observer relative in the case that Kolmogorov complexity depends on your preferred choice of Turing machine. You have to have a base layer for mapping, meaning onto consciousness forms this ultimate base layer. Well, I mean, aside from the consciousness question, which is slightly more deep and thorny, this is a very, very fine statement. I wish I knew who Will I am is. Maybe we could go into the Discord server and find him. But yes, I mean, I agree with all of that. Well,
just
thanks
show
for
me
that.
how they can join the community. I'll share the community link just in case they want to join our community. Look forward to discussing over the Discord. It'll be very useful.
And then we have another first-time chat, which seems to be go to dogehype.com.
Okay, yeah. Let me ban that. Let me ban that.
I hope it's a cryptocurrency. Dogehype.com. It's not framed as being a cryptocurrency, but I really hope that's what it is. Anyway, I guess Dogehype.com ended up giving some free advertising. And Criffy Tosp, whom I've seen on the Discord channel before, thanks for dropping in. We do have a channel on the Discord server for Sub-Axiomatic foundations, which, looking at it, I think it's mostly been. No, some people have participated, but yeah.
Let's continue there. Absolutely.
But Criffy, I always want to say Crispy Top. but it's Criffitas. If you if you have any questions, or if anyone on the stream or people who watch the stream subsequently have questions, you can always go to wolframinstitute.org, and then under the community page, you will find a link to our Discord server, and you can join, and then you can participate. Ask us anything there. It can be very elementary. We won't be mean. It can be very complicated. We also won't be mean, but we'll be mean for everything in between. Yeah. All right.
Very good.
All right, guys. Well, Carlos, thank you, and I guess I'll see you at the community forum. I'm not sure if we'll actually discuss. We'll have another formal live stream from this, but yeah, I look forward to seeing what you write, and I think we'll probably at least do some kind of email correspondence between now and the holiday season. All right, thanks, guys.
All right.
Cheers.
Goodbye, everyone.
Bye.